everyone. My name is Lynn Hua from IUTAM Brest in France. I will chair this afternoon session. So we're very pleased to have Jack Herring of NCAR to give the first talk this afternoon.
Thank you very much, Lynn Hua. And I again thank the organizers of this conference for inviting me again to this lovely place, this lovely city. This work, of course, is with Yoshi Kimura. You heard from him this morning. And in fact, he covers such a vast territory that I have only a little small part to play in this. So I have a lot of credit due him, so I don't have to work very hard because he's done the work. So here are the points that I wanted to cover, and I'm not sure some of them are probably not the things that are too much interest. I want to say about the third point, box limit on DNS. I'll come back to that at the end of the talk because to my mind, what you want to do in a DNS is to avoid scales which fill up the box. So if you imagine kind of cross section of the flow you're talking about, then you want to have all the flow, if you imagine contours mappings of it, all the flow in the middle of the box, more or less. If it gets to the edge, then you have a problem. You're just running into the walls of the box. The flow may look very nice, and if you make a carpet, a rug, out of this by duplicating those patterns all over the place, it'll go from one to the other. So you like the flow to be centered and not run into the walls of the box. So far, that's almost unavoidable, and I'll come back to that in a few minutes. In any case, here are the equations of motion, and I'm going to use this representation that Yoshi referred to, consisting of E1 and E2. I've superposed those directions and K on top of the graph I swiped from a book by Yost on Euler angles. So this is not Euler angles, but that's the way you would draw it in the XYZ plane. You notice that the equations of motion, which I've written in the middle of the slide here, and then the nonlinear terms I've just denoted by NL. But L itself is non-diagonal. It's anti-Hermitian. Of course, that means you can compute its eigenmodes readily. It's a simple thing. And C stands for cosine of the polar angle times the rotation rate. And S stands for the sine of the polar angle. Oh, here they are, times the stratification parameter. So we're going to put C equal to 0 in this study, and I'm going to refer to some way of representing such things. And here you'll see the most famous graph in the business, that of Maestrom and Ken Gage and others. And it's K-3 at low wave numbers. This is an atmospheric observation that I suppose is stratospheric range. And then roughly K-5 at the smaller scales. And the problem you run into is that as the Rossby number, as you go down, starting at the top of the K-5 range, and going down, the Rossby number keeps increasing if you compute it in a normal way until you get to the middle of that range, which you want to explain. And now you have no more influence of rotation. You have almost pure stratification. So the problem, which I think Eric Lindborg solved in some ways, is that you want to understand K-5 not as an inverse cascade, because apparently you don't have enough gas from rotation to make that viable by way of the quasi-dystrophic system. So you drop the rotation term in trying to explain this graph. And I think this graph was presented at a meeting, I think in Oregon, when Bob Creighton was there, and he's the one famous for the K-5 inverse cascade range to me. And he was shown this just fresh off the data center, and he was kind of non-committal. They wanted to invoke inverse cascade, and he simply said, "That's nice," or something to that effect, and didn't get at all excited. So I'm not sure he ever thought that this was his model was explanation of this spectrum. In any case, to try to understand that at NCAR, Doug Lilly prompted Olivier Mattei and myself in this paper here to try to do a simulation. In this case, it was 64Q. This is the old days. the data for these curves is transmitted by telephone, and I mean a real telephone. It's not anything in the ether or in the cloud, as they so to speak. You put down the phone, which is and you listen to the data, and you sometimes received pulses which were 10 to the 20th or something. You had to throw those away, otherwise you would have a problem analyzing the data. But anyway, so we tried this. We simply took Lily's two-dimensional calculations from 67 or so, and then we simply took a duplicate of that system 64 times. It is 64 this way and 64 in the XY direction. And then we simply forced it at wave number 10 roughly. And then we studied first to verify that you did get k minus 5/3 and an inverse cascade in the curve top marked A. Then satisfying that, we are not really looking at the forward entropy cascade, but mainly focusing on the inverse cascade range, which I think Lily certainly got right. Even the coefficient is reasonably got. And then we started turning on the stratification. And when you do that, you get a set of curves which I've illustrated in the lower section. As before turning on the stratification, of course, you have a box-limited calculation at the lowest wave number available. So what happens is the energy of the system gradually increases. It's beginning to pile up at lower and lower wave number. And that's what you see during the first half of those curves. The total energy, which is the top curve in each of these, starts gradually increasing. And at some point in the middle of the time zone, we turn on stratification. And then we see what the spectrum looks like over the same domain as we had before. And then if we didn't like that, or nobody liked it, then we turned on stronger stratification, exploring the whole range until we reached curve D, which is very strong stratification, much stronger than in the atmosphere. And you can see what happens the moment we turn on the stratification, the vertical, turn on the small vertical perturbation in the system, the total energy begins increasing, and that vertical dimension climbs up to a certain saturated value and stays there. The whole system then comes to a steady state. As you proceed down diagonally of these three curves, you go to stronger and stronger stratification, and always the lower curve is the vertical energy, and the one just above it is the horizontal energy. It always exceeds the vertical. So we were not able to, in this case, get the desired result. We didn't have inverse cascade for a three-dimensional system, which actually has energy in layers, as you know. So this was not successful in terms of looking at meteorological phenomenon, but it's an interesting thing to do, I think, and I don't know that it has been repeated by people now who simulate simulation codes of much higher resolution. There is an experimental setup by Brown and his group at USC, I believe. They have a big tank of some sort with stratified fluid, and then they bang on the side of it to excite these kinds of gravity waves and vertical vorticity. And if you sit next to that tank and you're a graduate student during those days, you would really have a problem. I've talked to someone in that category. I want to show, I'm going to come back to this, but Yoshi described a forced calculation in which the vorticity was developing into pancakes. And this shows, first of all, the usual isotropic turbulence. We turned off the stratification and let the energy dissipation climb to its maximum. And then we turned on at that point the stratification. And this was, so let me see if I can get that back. Here it goes. And you'll see the pancakes forming in the horizontal, and you'll see roughly what Yoshi showed this morning. But in this case, this is a natural kind of structure that the system wants to form, uninfluenced by any external random force. One thing I'd like to point out is that if you look at this carefully, and I'll show that next, in terms of the slide we just passed over, there's a picture of initial unstratified turbulence. This is the paper from which that's taken, and John Klein and Rodney James converted Yoshi's code, this was 8 or 9 years ago, to C++ code, and then designed a very nice way for ignorant users such as myself could run this very easily. So he's a very good programmer, in addition now a mathematician. So there's the unstratified case, and then this is the final state of the stratified case. And you'll notice in various places there tend to be kind of dipole doublets, if you like. You can imagine that they exist there in more abundance than perhaps in a random sense they should.
Are they vertically separated?
Yes, yes, like that, yeah. Yeah, you're looking from the side in this picture. Now, there's one more slide I'd like to show, which is a snapshot of a certain region. We were interested in this particular pair of vortices here. And so I asked John Klein to blow that up. He could do that in maybe just a minute. And this is what he found. You have these structures. This is looking down on it, this doublet. And this is on the horizontal. So you have these very thin, if you like, pancakes with edges which are not necessarily smooth. They're sharp in certain regions. So one more point about decaying turbulence, about the papers of Fincham, Maxworthy, and Spedding, for example, some 12 years ago, I guess. They imagined that these structures existed like that, where the pluses and the minuses designate the sign of the vorticity, and that if you imagine the vorticity line goes through these structures and shuts away that the center is spinning in the horizontal, then that is the vorticity is vertical. Then you come to the edge, and it makes sharp left or right turns, like so. And they imagined that this would be useful in describing some of the dynamics of the flow, but I have not really seen that done. They said that this configuration, number 3, was outnumbering the other kinds of configurations, and that's about all I know about it. But what conclusion they reached, in part, at least a speculation, they said that this tendency for vortex lines to connect from one layer to the other explained some aspect of stratified turbulence, which is not like two-dimensional turbulence. If you have strictly two-dimensional turbulence, and imagine these layers are independent, they can wander wherever they like. And in that case, they become very isolated, one far from the other. Whereas in this case, they thought that this a way of analyzing the flow would indicate that the vortex patches could not wander very far from each other. That makes for a less intermittent kind of flow. I don't know. It's hard to say whether this kind of structure is less intermittent than the other. There are certainly holes in this, places where you don't see much activity at all. But in anyway, that's what I think. So that flow decays, and this is the actual data. It decays very accurately, like T-1 over the final. Here it is. The total energy as a function of time. It drops like that during this whole portion, when the energy drops by more than a factor of 10. It's T-1. So that's one thing, perhaps, to try to explain about such flows and when they decay. And I want to say again that indicates flows which structures which are natural to the kind of stratification you impose. There is a nice paper by Prode and Fincham and Samaria, and one issue of I'm not sure where this is physics. No, it's journal JFM or it's JFM, isn't it? That right? Okay. In which they observe the decay rate roughly, and this is the thing they like: the energy of this stratified flows, which has a rather low Froude number, decays like the spectrance. The time dependence is t to the minus 1.3. That's like normal turbulence, and I'll come back to that point in a minute. So here are some more of their data, and I'll just go through that rather quickly. And so how do you understand the decay law, which is T-1? If you go back to Komolgras, analysis which gave T minus 10/7 and isotropic turbulence. That's based on the fact that in the low wave number range, the spectrum goes like k4th power. That's the permanency of large eddies in Bachelor's terms. And then you have k minus 5/3, then a kind of exponential dissipation range, at least at moderate values of the Taylor-Reynolds number. So you then do two things to get the answer. Is you assume that you have an equation, of course, defining the energy decay. You assume that you take it that A is constant. The coefficient of k4th, that is just constant. It doesn't vary in time. And this was illustrated very nicely recently by Yukio Kaneda and Peter Davidson. We can it was unsettled for a long time whether this A was absolutely constant or not. But now, experimentally, numerically, a huge numerical simulation, which was done, by the way, at low Reynolds number and to avoid running into the box size where something else will happen. It indicates a very constant value, constant. So that's now, at least in such a situation as this, pretty well understood. And you can then ask, for example, suppose the flow is box limited. That is, when you plot the energy, the maximum of the energy is as the smallest wave number available. So you imagine the pattern has filled up the whole box. In that case, Bob Kerr will tell you that the energy doesn't decay like 10/7. It's like T to the minus 2. And people at Oregon, University of Oregon, have also observed that now experimentally at low temperature flows. So that's the story there. And we are always using the energy decay law and some form of k minus 5/3 in this range here with a proper epsilon. So the goal is to use those equations with constant A and this kind of value of energy at low wave numbers to solve for the epsilon, which is d by dt of the total energy. I want to say a few words. I'm going to come back to this in a minute. Suppose that the energy decays like k minus 2. You could then go through the same calculation. You get a decay rate like that, which is actually halfway between two-dimensional turbulence, which doesn't decay at all, and three dimensions, which has a coefficient T to the minus 10/7. Just take the average of those two, and you get this law. Now, if you run into the box size, so the E goes like that, you obtain T minus 1. So this initially made us rather happy because Yoshi's simulations always gave this for strong stratification, even for 256 cubed simulations. I'm not sure that this holds at all at large Reynolds number, because as you begin to go to higher and higher Reynolds numbers, and such that the buoyancy Reynolds number is large enough to prevent collapse of the flow, you pick up, as Eric will tell you, a k minus 5/3 range, and so you'd have to add that to the analysis that we just went through. And when you do that, you'll find that the k minus 5/3 contribution to epsilon, the total decay rate, always exceeds that lower portion of the curve, which is proportional to k minus 2. So what Fincham and others observed in the experiments that conforms to that, probably T minus 1.3 or so is what you would obtain at large Reynolds numbers. And I'm not sure their Reynolds numbers are very large, but in any case. I want to come back to this slide in a few minutes. Now, let's look at the flow that obtains when the system is decaying. So you pick up perhaps a natural state of affairs that the turbulence likes. Yoshi did some analysis of the distribution of vorticity, or squared vorticity, as a function of the polar angle. And then you see that at very low stratification, 0, is more or less constant throughout the angular domain. 5 minutes, thank you. And if you go to very high stratification, it tends to saturate. in these wings, we thought for a while that that's all the whole story. And for that reason, you could simply say that as stratification increases beyond a certain point, the degree of anisotropy does not. And this shows another aspect of the flow, which is distribution function for the vertical, the acceleration, and for stratified and unstratified cases. And you'll notice that the unstratified case has these exponential wings, a very non-Gaussian fall off, whereas with stratification, you pick up these blue pattern for the vertical gradients and the horizontal for the horizontal motion field, and they're very Gaussian. So it could be that these theories that were mentioned this morning, this is the same kind of curve for the distribution of vertical shear, du by dz, and this was done earlier on by Olivier Mattei. There is the unstratified case, and there is a stratified case. So you have some reason to think that flows, situations based on Gaussian assumptions or near Gaussian assumptions for the PDF of the system could be closer to Gaussian than for unstratified turbulence. So life is a bit easier. I want to show a few graphs at the close of the spectra we obtained in terms of the phi1 and phi2 description. And you'll see here is a forcing wave number at 5 or so. And as the time goes on, these converge to a kind of almost isotropic small scale structures, the temperature following the phi2, the wave modes accurately in that case. But if you look at the isotropically averaged system, in this case at 512 cubed, we didn't have any signature of inertial range of power laws at all. Everything looks different in this case between the horizontal and the vertical modes of motion. So let me skip that because I have only a couple of minutes, I suppose. So I want to say a word or two about the this law here, if there is such a thing, in terms of trying to model it with one of these closure theories. And I'll remind you that the closure theory here is really a kind of random walk characterization of the turbulence. That is, if you want to know the response of the system to dissipation, you take the square of the force, which is like u dot grad u. You square it in some way and take its wave number component, and then you divide it by the time, or multiply it by the time the force acts. That's always what you do when you describe things by Fokker-Planck or random walk problems. So that's the way you're estimating the turbulence. You need one other. So the turbulence time scale is like this, k cubed e of k. And the other thing is that when you evaluate this integral from getting the epsilon and the value of your spectrum and the inertial range, you make one other assumption, which states that this term here is local in wave number. In other words, the spectrum is not so steep that you have to consider broad ranges of wave numbers, but you can just look at the wave numbers near the one you're talking about. So making those kinds of assumptions, you get k minus 5/3. And the point I want to make here is this: if you now go back to the kinds of time scales during which the flow lasts, you have to add the turbulent time scale, or rate of eddy turnover time, or reciprocal of that really. You have to add that to the Brunt-Weissler frequency here. That's not quite the whole story. It's rather complicated when you go through it. This should be n sine theta, and what you're doing when you look at the calculation is averaging over various angles. So you're looking at a dispersive wave analysis of these kinds of equations, and in effect, I think it gives something like that. And then when you do that, finally you obtain an equation like so.
It's the first time that, I mean,
What?
nobody before made this argument.
Zeitling did, didn't he?
Huh?
Where is he? Usually in the
I
back.
mean, to get K
Yeah,
minus to it in this way.
Didn't you do that with your student?
What?
No, it's not exactly that. But
Okay. George Carnevale knows the answer. It was just due to Greg Holloway, I remember some analysis of his like that. So anyway, So this is try to lend support to the K-2 range that that was described this morning, that Kimura described this morning. To my knowledge, this hasn't been done in terms of the kind of analysis that looks into detail. This paper here by Galperin and Sukuyansky did do that with the kind of ED-QNM analysis. They called it normal, what is the quasi-Gaussian approximation to the cumulus to get that sort of equation. And then finally, there are other works which Lindbergh and company look at this from an entirely different point of view, which analyzes things in terms of the vertical and horizontal anisotropy, and he can tell you that much better than I can. Here's a final curve which I'll show, but we were very frustrated at one time in looking at this region, which is supposed to be constant at low wave numbers. And so we did a calculation in which the viscosity is simply put to 0.
What's on the x-axis?
Oh, here. I'm sorry. This is the energy as a function of wave number. Sorry. So what you see is as flow goes on, it develops into a K4th region, which it likes. And then in the intermediate region, it develops K-5/3, and that coefficient is really the right coefficient. And then eventually you get K squared. K squared is the thermalization component of the spectrum, and it simply it really sits there. It doesn't transfer energy anywhere, so it doesn't do any damage to include it. So that was very strange to me at first.
It's a pile-up. I mean,
It's a pile-up, yeah. It'll eventually take over the whole thing. So the idea is you do a calculation like this for a while. You look for signs of inertial ranges. You analyze the energy transfer, or maybe the flux. And then, depending on the problem, you pick up whatever kind of inertial ranges may exist in the system. If it, for example, is rotating or stratified flows, it could be that you'll reveal here the different anisotropy degrees in spectra in the intermediate wave number range. And here, you could pick up equipetitioning of the components that you're talking about, which would be roughly K squared and different coefficient depending on different spectra that you're looking at. So that has not been explored. It may be interesting thing to do, which is rather novel, and it's been stressed recently by Uriel Frisch and others that may be a good way of doing things. So here are the concluding remarks, and perhaps, as I say, viscous flow like that would be interesting. Here's the conclusion that Yoshi reached. There are two regions of the spectra, at least for the vertical component, K-2 followed by K-5/3, and we've tried to indicate roughly how a calculation like that would go, although the details need vastly filling in. Maybe Claude Cambon by now has done that. So I think, though, in order to have flows whose scales are naturally selected by nonlinear processes, we need much higher resolution, maybe 4,000 cube, like Yukio Canada does, to resolve this sort of issue. So I'll stop there. Thank you.
Thank you, Jeff. There's time for questions.
I just want to make a remark. Why would you try to quantify, those nice pancakes, etc., which would need, let's say, 4-point correlation function?
Yes.
Let's go beyond second and third moment. And then, by making 2 points like this or like that, you can really quantify how pancakey, how layered you are. That's what, by the way, people did for magnetic things, when you have stripes.
Okay.
You try to quantify pancakes.
Yes. I think what you say sounds right.
Another question or comment?
The energy going like t to the -1.
Yes.
Is there any theoretical or numerical reason to think that should be independent of stratification?
You mean the power law of T?
Yeah, of energy.
No, I mean, once K-5/3 takes over, it changes. But if you have a limited domain, with these calculations had, then then you may expect T minus 1, according to the analysis that briefly it showed. On the other hand, there could be other reasons, and I'm not suggesting that's the right reason, because the flows could be, they have to be box limited in that case. Otherwise, you'd find 5/7 perhaps, or other kinds of laws like that. But the analysis hadn't been pushed to a kind of rigorous conclusion, even in those kinetic theory approximations that I've described. Yes?
Would you be less box limited if you took a shallow domain this way? And
You would, yeah, but in this direction,
Yeah.
what
So
do
you
you?
wouldn't have to go to 4,000 cubes.
Not necessarily, no,
Yeah.
but somehow to be convincing, I think you have to include all the manner of possibilities for the vertical layering to take. But that's certainly the first thing you would do if you don't have 4,000 cube available.